Chapter 28, part 2. But before we go to part 2, I would like to go over another way of solving this problem. So remember that we found what the value for sine is. So sine theta is 3 times 664 times 10 to the negative 4 over 12, right? So based on that, if I can write it down again, sine theta is 3 times 664 times 10 to the negative 4 over 12, which is 664 times 10 to the negative 4 over 4. Okay, this 3 and 12 will cancel out. So what we have is, if you put this in your calculator, I just did it, and I ended up having 0.0166. That's what I had. So based on that, I can find theta, and theta is sine negative 1.0166, okay? And this gave me an angle of 0.95115 degrees, okay? So this is the second way of, maybe solution, okay? So that's the theta, and tan theta, the tangent of theta, is y over L, right? Because if you imagine that this is our, this is L, this is y, and this is theta. And so y is L times tan of theta, right? So y is 2.75, which was the distance, or this L, times tan of theta, which is tan of 0.95115 degrees. So we ended up having y equal to if you put this in your calculator, I've already done that, 0.0457 meters. So that's the final answer. So now let's go to part 2 of the video and continue our work on chapter 28. So single slit diffraction. If you have a single slit diffraction, you are still going to see patterns, and that's how the law that is governing that is called Huygens principle. So if I have a plane wavefront that's coming to this doorway, and these are walls, and this is the doorway, we believe that every single one of these wavelets is acting like a source of wave, okay? So in other words, if I wanted to show it like that, if this is the wavefront, then every single point is acting like a wave source for me, or a source of wave. So kind of like that. All of these points is acting like a source for me. All right, so every point on a wavefront acts as a source of tiny wavelets that moves forward with the same speed as the wave. The wavefront at the latter instance is the surface that is tangent to the wavelet. So now, if you consider all of these points, all of these wavelets to be the source, then they will create wave, and the wavefront, which is this blue line here, is curved on the edges. So there is a curvature right here and right there, and that's why the observer or the listener can hear sound that is coming from doorway. The observer is on the corner of the room, but he or she can still hear what's going on in the door because of this curvature that's happening in the wave. Okay, so you have a plane wave coming in. All of these wavelets is acting. All of these wavelets are acting like a source of wave. So then you have another wave front, and there is a curvature on the edges. Okay, since the plane waves conforms to the curved shape of the wavelets at the edges, the wave curves around the edges of the doorway, and the person who is not in front of the door can still hear the sound. Okay, so because of this curvature over there. And there is a very interesting ratio between the wavelength and the doorway size. So if we consider the doorway size to be W, and the lambda is the wavelength, okay? So lambda is wavelength. Okay. And so if if lambda over W, if you consider the ratio of lambda over W, for the small values, we have something like this. You can see that there is almost no destruction towards the wave. There is still curvature on the edges, but the wavefront is still going on. So you have continuing of the pattern. But if you have a lambda over W ratio of a very, very large number, so if this one, the lambda over W ratio is large, then this slit will act like a source for us. So you'll have your wave is still going forward, but you can see that there are huge curvatures. Here you have a plane wave coming in, but you will have a curvature in your wavelength. So Huygens wavelets are predicting, and in fact the experiments have shown that they are doing that we have a midpoint of a central bright fringe at this center point, because all of these wavelets, all of the rays that are coming from these little sources are meeting each other constructively at this point, because they're all traveling the same time in the same path to get to this point. So at the center, we'll have a huge bright spot because all of these waves are meeting each other there constructively. All the wavelets travel the same distance, and constructive interference create a very huge bright spot at the screen. So this is how it would look like. We have a single slit, okay, or a doorway for the light to go through. So then we'll have a huge pattern at the center. We have a huge bright spot, but then we have smaller, darker spots to the either side, either top or bottom, or left to right, whichever way you want to look at it. So monochromatic light passing through a single slit has a central maximum and many smaller. We have a central maximum and many smaller and dimmer maxima around it to the either side. Okay, and this is what the drawing we say. And then, so the diffraction grating creates evenly a space line that dims slowly on the either side. We know that already. But we know that the central brightest spot is at least 6 times higher than what we see here. So we expect to see a very huge, high intensity brightest spot at the center of the location on the screen. Okay, so it's at least 6 times higher than what we see here. So single slit destructive interference, as I said, there are darker spots, but let's talk about those dark spots as well. So, so a single slit destructive interference, what we have here is that these drawings are showing those first dark fringe or first dark spot, and let's talk about why this is happening. So these drawings show how destructive interference leads to the first dark fringe on the either side, as I said. So we consider 5 wavelets or spots or sources, but they could be many of those, correct? So since the light rays are parallel, all of these light rays are parallel, okay? They each make the same angle theta with the horizontal. So in other words, if the central one with respect to this dashed line is making an angle of theta, then this one is also making an angle of theta, this one is also making an angle of theta. All of them are making the angle of theta with respect to the horizontal or dashed line. So this is also theta, okay? Wavelet number 1, which is top right there, have the shortest distance, is wavelet number 5 travels the longest distance, okay? So we know that because we're looking at the picture. But here's the crazy part. If the difference in the distance is one wavelength, so from 1 to 5, from top to the bottom, if the distance from the path is one wavelength, which is right there, okay, so let me highlight that. All right. Then, if it's one wavelength, then we have the first dark fringe as a destructive interference. So wavelength number 3, okay, and 1 are out of phase. Similarly, 2 and 4 are out of phase. So each wavelet from the upper half of the slit cancels the corresponding wavelet from the lower half. So we get the darkest spot or destructive interference. Now, remember from our previous double slit or Young experiment, from our Young's experiment or double slit, what we have for bright spots, we have sine theta being equal to m lambda over d, with m being 0, 1, 2, and so on. But here for the single slit, sine theta m lambda over w, and w is this whole distance of the doorway or the whole distance of the slit, or the length of the slit, m lambda over w gives the condition for a dark fringe. They are similar. For the Young experiment, this will give us the bright spots, okay? But for the single slit, this is giving us the dark. So this is the single slit. Okay, so for the single slit, m lambda over w, and w is the distance of this doorway or the length of the slit. This will give us the first, or the dark fringes in the single slit diffraction. We will only consider the single slit destructive interference in this class. So I'm not going to ask you about the constructive interference. So no constructive interference here. So a system of with a large number of slits is called diffraction grating. You've probably seen this before in your previous science classes, but just a review. So if you have a system of a large number of the slits, this is called diffraction grating. And as a number of slits grow, so from going from 1 all the way to maybe 20 to 30 to 100 or even more, the peak becomes narrower and more intense. Here's a diffraction pattern for 5 slits. So you have M1, and then you have 3 little smaller, less intense, bright spots, and then you have another huge bright, and then you have another huge bright on the left, and they are symmetric, by the way. So these are less bright spots, but then you have 3 bright spots at the center, and these are destructive. Okay, so these are destructive. Okay, and these are constructive, and then smaller constructives right here. Okay, so constructive interference for diffraction grating. So if let's say that I have 5 slits, 1, 2, 3, 4, 5. So this is my source 1, source 2, source 3, 4, and 5. So the wave are coming in. These are the rays of wave, and they are parallel to one another. But as soon as they get here, they will start to look like a source themselves, right? So source 1 is getting lights like that. Source 2 is getting light out like that. Source 3 is doing the same thing, so on and so forth, right? So the position of the peak are different for different wavelengths of light. So depending on the wavelength, now you'll have a different position. One more time, the position of the peaks are different for different wavelengths of light. The condition for constructive interference in the diffraction grating is that sine theta being equal to m lambda over d, and d is this distance, okay? D is this distance between one slit to the other. So this is D. All right. And then in this M, because this will be symmetric, M is either 0, plus and minus 1, plus and minus 2, and so on and so forth. So if you are using, so previously in our previous examples, or the things that we have seen, for example, in a Young experiment or in a single slit experiment, we have seen a one single light color, for example, a red light or blue light or whatever, with a single wavelength, okay? For example, in the previous problem, we used the wavelength of 664 nanometers. But this could be done for the white light. So the diffraction grating is as I said, is a large number of evenly spaced parallel slits. So you can see there are 5 here. Light passing through is diffracted in a pattern similar to double slit, so similar to Young experiment for the diffraction grating, with the bright regions at various angles. The pattern obtained from a white light, this is what I was going to talk about, white light, incident on the grating. So this is white light coming in, white light going in. The central maximum is white, so this is very important. The central will always be white if you have white going in. All right, the central maximum is white. And then you have a higher order of dispersed white light into the rainbow. So you'll have a first order rainbow on either side, and then you have a second order rainbow, less intense on the either side, similar and symmetric location from either side or left to the right. So this has a very interesting application. We can take a look at the spectrum of light that we get from the sun. So a diffraction grating can be used to separate light into a spectrum. We know that spectrum of light is something that we are, particularly physicists and astronomers, are really interested to. So the greater the number of the slits, the better the resolution. So if you're dealing with, for example, a grating of let's say 200 slits per millimeter, then you have a better resolution to compare to 5 slits per millimeter. Okay, the figure below show our sun in the visible light. So the visible light, let me go back to pen. So visible light is from 400 nanometers to 700 nanometers. Okay, and then B, using the diffraction grating, we see the spectrum of light using the diffraction grating. So all the way from blue to red. So take a look at this question. Using a diffraction grating with 200 slits per millimeter. So we have 200 slits in each of these, in each millimeter. Okay, so 200 slits per millimeter. That's what we have to create a diffraction pattern on a screen 2 meters away. So L is 2 meters. 2 meters away is our screen. You see bright fringe 170 millimeters apart. So the Y is 170 millimeters, okay, apart. So what we're looking for is what's the wavelength of the light? We're looking for lambda. Okay, so that's what we're looking for. So now let's take a look. We have a 200 slits per millimeter. It means the distance between the slits from one slit to another is 1 over 200, okay? This is 1 over 200 millimeter, which means it is, so this is slit per millimeter. So this will give us 1 over 200 will give us 0.005 millimeter per slit, which means that if this is our first slit and this is our second slit, for example, the distance between them, D, is 0.005 millimeter. Okay, so in other words, if I want to write it correctly in this SI unit, D is 5 times 10 to the negative 6 meters. All right, so knowing that, we can find theta. So let's take a look. I have a triangle here, right? Maybe I can draw a better triangle next time. Let's see. Yeah, should be good. All right, and I can probably just rotate that around to have what I want. So here we go. Awesome. So what we have here is this. We have theta here. We have L here, which is 2 meters away. So that's 2. And then we have Y, which is already given to us by the problem, 170 millimeters. So we can find theta. So theta is tangent -1 of Y over L, okay, which is tan -1 of 170 times 10 to the -3 over L, which is 2. And this is, if you put it in your calculator, you can find that it is 4.85 degrees. So we know the theta from this slit to the points. So we have bright spots, meaning that we have constructive interference, right? So we can use sine theta being equal to m lambda over d, okay? So lambda is d sine theta over m, which is, d is this distance, which we have it already, 5 times 10 to the -6. Okay, and then we have sine of lambda, sine of theta, and we have the theta, 4.85 degrees. And then this m goes from 0, 1, 2, 3, right? M is 0, 1, 2, 3, and so on. So if it's the first bright spot, you see bright fringe 170 millimeters apart. So the first one is 1, and for the first one is 1, which is 170 away. So this will give us lambda being equal to, if you put this in your calculator, you will get 4.23 times 10 to the negative 9 meters, okay, which is 423 nanometers, which is violet wavelength. Okay. So here is the center bright and here is the first bright. Okay. Now let's take a look at another example. Example number 3, light with a wavelength of 655 nanometers. So this time we have the wavelength already. So lambda is 655 nanometers, 655 nanometers. Okay. Let's see. Shines on a diffraction grating with 255 slit per millimeter. So the slit is 255 slits per millimeter. Okay. You see bright fringes on a screen that are 195 millimeters apart. So in other words, y is 195 millimeters apart. How far away is the screen? Now we're looking for L this time. We're looking for L to find L. Easy peasy. So what we have is this. We have, again, that's what we have, right? So this is L, this is Y, and this is theta, and we're looking for this L. Okay, so we have bright fringes. This means that we have constructive interference. So right, so this means we can use this formula. Sine theta is m lambda over d, with m being equal 1, for example. Okay, and we know what d is. D is 1 over 255, 1 over 255 slits per millimeter, which means that we have, if you put this in your calculator, 1 over 255, you'll get 3.92 times 10 to the negative 6 meters, or you will get 0.00392 millimeters, okay? So lambda is 655 nanometers, which is 655 times 10 to the negative 9 meters, okay? And y was 195 millimeters, which is 195 times 10 to the negative 3 meters. So I'm turning everything to meters so I can use them. And this would be 3 times 9.2 times 10 to the negative 6 meters. So I turn that to meters as well. Now, let's get theta first. So if I want to get theta, theta is sine negative 1 of m lambda over d. All right. So sine negative 1 of m. M is 1. So this guy is 1. All right. So 1 times lambda, which is 655 times 10 to the negative 1, 10 to the negative 9. And d is the distance, which is right there, 3 times 9, 2 times 10 to the negative 6. So this will give me 9.6188 degrees. Okay, so that's the theta. And now we have the tan. We can use tan of tangent. Tan of theta is y over L. Okay, so this means that L is y over tan of theta. And thus y, we have y 195. So 195 times 10 to the negative 3. Tan of 9.6188 degrees. So at the end, L is 1.15 meters away. 1 meter and 15, 1.15 meters away. So let's talk about thin film. So if you have light striking a thin film, a portion of it will be reflected, which is ray 1. So if you have an incident ray coming in or incident light coming in, a portion of it will be reflected, okay? And a portion of it will be refracted, okay? So this is medium 1 with the index of refraction of N1. And then you have a thin film with a thickness of T, for example. This is the thickness of the film, which we showed with T here. And it has an index of refraction of N2. So the refracted ray is partially reflected at the bottom. So this refracted beam here will be reflected at the bottom and emerge as ray 2 right there. So refracted, reflected, and then emerges ray 2. So we have ray 1 and ray 2. These rays will interfere in a way that depends on the thickness of the film. So this ray 1 and ray 2 will interfere either constructively or destructively, but then this depends on the thickness of this film here, or the thickness of medium number 2. Okay. So not only the thickness is important, but also N1 and or N2 is also important, because we have seen it in chapter 26 and how they are related to one another. Remember Snell's law, N1 sine theta 1 is N2 sine theta 2. Okay. So because of a reflection and a refraction, 2 light waves enter the eye when light shine on the film or a thin film of gasoline floating on a thick layer of water. So if I have a thick layer of water with an index of refraction of 1.33, but I have a gasoline on top of that with a thickness of T with an index of refraction of 1.4, and then I have air on top. So the incident ray or light will come in, part of it will be reflected as ray 1, part of it will be refracted, and then that refracted beam will be reflected and then going as ray 2 to our eyes. So these two ray 1 and 2 will have an interfere, and based on this thickness and this gasoline in this index of refraction, these two will be either constructively or destructively. So because of the extra distance travel there can be interfered between the 2 waves. So because of this extra travel time, so ray number 1 is getting here, but ray number 2 is going all the way down and then going all the way up, and then so it's traveling extra length. The brightest spots appear if constructive interference occur. A darkest spot occurs if the destructive interference occur. And the additional distance traveled by the light ray occur in the film. So we know. So we need to know the wavelength of the film, okay? So the lambda in the film is lambda in the vacuum over n. And this is in fact coming from the fact that the velocity is c over n. Okay, the velocity in that medium or the thin film is the speed of light in vacuum over n, or the index of refraction of that thin film. So almost the last part of our, we're in the home stretch of our chapter. So when the light travels through the material with a smaller refractive index towards the material with a large refractive index. So from n, which is a small, towards n, which is big. Okay. And then the reflection at the boundary occur. Reflection at the boundary occur along the phase change. Along with the phase change. This is very, very important. So this is important. Okay. Along with the phase change that is equivalent to 1/2 of the wavelength, or 180. Okay. In other words, if you have an incident wave going in, okay, and so the phase is pi over 2, positive pi over 2, but once it's being reflected, because of this, this medium number 2 has a high number or a high value for high or large index of refraction, then you will have a phase change of 180 degrees. So it was pi over 2 at the beginning. Now it is negative pi over 2. So the phase will change 180 as a reflected way. Light waves travel from a large towards a smaller refractive index. There is no phase change upon the reflection. In other words, if this is not a high or large N material, then nothing will happen to your wave. So multicolored thin films. So under natural conditions, thin films like gasoline on water or the soap bubble on the figure that you can see have a multicolored appearance that often change while you are watching them. Note that here we have removed the blue light. We'll talk about that. But why are such films multicolor, and why do they change with time? Okay, the answer is in next slide. So in our examples so far, we have seen that destructive interference occurs such that the blue light is removed from here. And this depends on the thickness of the film as well. So we can see different colors depending on the thickness of this film. So depending on what the thickness of this soap on the water is, we can see different colors. If the colors change as you're watching them, it's because the thickness is changing by time. The thickness is changing by time. So if the colors changes as you're watching the film, that indicates the thickness is changing by time. So this thickness is changing by time, and that's what the answer was. Everything depends on the thickness and the index of refraction of this thin film. Also note that the color depends on the angle with which the light strikes. That's true. If the light rays enter the film at a large angle, it will travel further and thus change the wavelength of the light for which interference occurs. So not only 3 things are important. Okay. 1, N. 2, thickness of film. And 3, the angle of light that's going inside the thin film. If it's going with a different angle, so we have a different phase change. So as I said, if the light rays enter, let me highlight that. If the light ray enters the film at a large angle, it will travel a further and thus change the wavelength of the light for which interference occurs. So this is the end of chapter 28, and let me know if you have any questions.